Hello everyone and welcome back to Nunley Math as we continue our discussion of radicals and radical expressions. Today we're going to talk about dividing radical expressions, and you can see I actually have called this dividing radical expressions 1. Ordinarily I would do this entire lesson in one day in class, but I think using distance learning it's a little more difficult to cover all of these ideas at once. So I'm going to split this up into 2 lessons over the course of a couple of days. Again, notice if you're in my class that the assignment here is a little on the long side in terms of the number of problems, but in terms of how difficult the problems are, these should be pretty quick problems for you to get through. So I'm not overly concerned that you're going to have trouble spending and end up spending a lot of time on this. So let's go ahead and get started. I think this is going to be a shorter video for you today because a lot of what we're doing is going to be based on the ideas that we've covered in the last 2 previous videos, and it should all flow together very nicely conceptually for you, I think. So consider this. If I give you the square root of 100/4, you have a fraction under your square root sign. Order of operations says that this square root would act like a grouping symbol, meaning we should do the division first. So 100 divided by 4 is 25, and of course you know the square root of 25 is 5. But I want you to think about this. If I were to write the numerator under a square root, and I were to write the denominator under square root, and I were to use this division bar as my grouping symbol, meaning that I should do everything on top first, everything on bottom second, and divide last, you'll find that the square root of 100 is 10, and the square root of 4 is 2, and that 10 divided by 2 is 5. Now, that shows us that the square root of 100/4 is the same as the square root of 100 divided by the square root of 4. And this should make sense to you because this is very similar to what we did with the product property for radicals, which basically said that if you square root the whole thing, it's the same as square rooting the individual pieces. In fact, I have it written out for you this way. The square root of a quotient is equal to the quotient of the roots. That sounds pretty confusing and complicated. But basically, if you have a square root with a fraction underneath, you can take the square root of the numerator and take the square root of the denominator separately and get the same result. Here's another example of this, just to clarify and make sure we're all on the same page. The square root of the fraction 144/36 is the same as the square root of 4. 144 divided by 36 is 4. We should do the division first using order of operations, and we know the square root of 4 is a 2. But if I were to take the square root of the numerator, the square root of 144, and then take the square root of the denominator, radical 36, and divide last, well, I would get 12/6, which is also 2. It doesn't matter which way you do this. Both of them are acceptable. Sometimes one way is going to be more useful or helpful for you than another. There again, 2 quick examples to give you the basic idea of what we're doing here today. The 2 are the same. So let's make this a little more interesting. If I have the square root of 36 over 25, I can split that and make it radical 36 over radical 25, which is 6/5. There again, the same thing we were doing on the previous slide. But if I give you something like radical 12 over 27, more than likely, you're not going to want to split this into 2 right away. More than likely, it's going to be easier for you if you simplify the fraction first. This is 4/9. Notice 12 and 27 can both be divided by a 3, giving you 4/9. Because once you've done that, you can see that the numerator and the denominator are perfect squares. And so we just square root the numerator and the denominator, and we get 2/5. I'd recommend that you pause the video and try this one on your own. I'm going to assume that if you wanted to do that, you've already done it, and now you're watching for an explanation. Again, I'm looking at this fraction, and I'm realizing that 2/32 will simplify and become 1/16. And then I'm going to square root the numerator and square root the denominator separately and get 1/4. Here's another one. Again, pause the video, try it, and then restart the video to see if your answer matches mine. I'm going to simplify, this fraction first and get square root of 9. Notice that when I do that, it comes out as a 3. This is an example of when it's easier to simplify first than to square root the pieces, because radical 27 would give you something fairly complicated. Radical 3 would also be an irrational number. Here's an example where it might be better for you if you have a square root on the numerator and a square root on the denominator. It might actually be better for you to write it as a single fraction before you simplify it, because this is not a perfect square, this is not a perfect square. But if I turn it into a fraction and simplify, it becomes a perfect square. The square root of 25, of course, is 5. Keep in mind, sometimes it's easier to split it into pieces, other times it's easier to put it together. The way I usually tell is I look to see, do I have perfect squares already? And then I look to see if I were to divide or simplify, would it be easy, or would it give me a perfect square? This one's getting a little more complicated. I would probably go ahead and write this as a single fraction. The reason I would do that is because I can look at this and see 30 over 6 is going to simplify, as well as a cubed over a squared. Notice when I put it together, 30 over 6 is 5. A cubed over a squared, the rule is we would subtract those exponents, leaving you with a to the first. So this becomes radical 5a to the first. Notice we didn't write the 1 there. It is okay to leave this in this form since neither of these are perfect squares. How about this? I look at this, I can see 40 and 10 are going to simplify, the b's are going to simplify, so I'm going to put this together as a single fraction. 40 over 10 is 4. B to the 5th over B to the 2nd is B to the 3rd. So this becomes the square root of 4B to the 3rd. Notice though, the 4 is a perfect square and B to the 3rd has a perfect square inside of it. We're going to have to simplify this some more. Square root of 4, square root of B squared, and square root of B. Remember, every even exponent is a perfect square. The square root of 4 is 2. The square root of b squared is b. Remember, it should be absolute value b, but we're ignoring that for the rest of this unit. And then I can't do anything with the square root of b. So I get square root of 4 is 2, square root of b squared is b, and then the square root of b I can't do anything with. Last one. Again, for me, it's probably easier if I put this together. I happen to notice that 40 over 5 is going to give me an 8. X to the 4th over x cubed. We're going to subtract these and get an x to the 1st. Y to the 5th and y cubed, we're going to subtract these and get a y to the 2nd. So the square root of 8xy to the 2nd. I need to make sure this is in simplest form. I happen to know there's a 4 hiding inside that 8. That's a 4 times 2. This is already x to the 1st. Y squared is a perfect square, so I'm going to have to deal with that. Notice I split the 8 into 4 and 2. I can take the square root of the 4. That's going to become a 2 on the outside. I can't do anything with the 2. I can't do anything with the x, but I can square root y squared and make it just y. Notice the 4 goes to the outside as a 2. The y squared goes to the outside as a 2. And I leave the 2x on the inside. As always, thank you for watching. We wish you all the very, very best of luck. Make sure you hit that like button. Make sure you ring that bell to turn on your notifications so you can keep up with all the things coming out of Nunley Math. We wish you all the very best. Take care of yourselves.